Hi class. So welcome to the next lesson. So this is going to be deep learning. Now I'm gonna give you guys. We're gonna go on the surface of deep learning. Deep learning goes. There's so much more uh, tools that we can use or information that we have about deep learning. But we're gonna go right now in the surface of it. I'm gonna explain to you guys what is the idea of deep learning, and we're gonna do a simple case of deep learning. Again, there's so much more depth that we can learn about deep learning, but I'm just gonna give you guys a rough idea because we want to stay in the scope of the class. Okay, so we talked about artificial intelligence, but remember that artificial intelligence is the ability of a computer to perform tasks commonly associated with the intelligent beings. So Alan Turing um, is one of the greatest mathematicians and computer scientists, one of the pioneers of digital computers. Defined the rules of artificial intelligence, and he said that, in a sense, practically, if you interact with if you have a curtain and one side you have a human and the other side and another side of the curtain you have a computer, and you can't see them, but you ask them a question on both of them, right? The same questions, and you don't know which one's which. You don't know which one's the human, which one's the computer. If uh if the answers when they return, you can't tell who is the computer and who is the machine, that is artificial intelligence. That's how he defined artificial intelligence. Okay, so like it says here, the ability of a computer to perform tasks commonly associated with the intelligence of a human being, right? Of beings, not just humans. Machine learning. We talked about machine learning a lot. I mean, one of the concepts that we learned in this class, this course, is machine learning. But machine learning is the study of algorithms that learn from examples and experience instead of relying on the hard code rules and make predictions on new data. So we don't hard code the the algorithm, the program, right, to answer the questions. It is learned by itself. So throughout learning, a process of learning, the machine can answer the questions and make predictions of the data. Now, what is deep learning? So deep learning is a subfield of machine learning focusing on the learning data representation as successive layers of increasingly meaningful representation. I'm going to give you guys an example of what that means. But let's look at the big picture. Artificial intelligence is the bigger field in computer science. And within artificial intelligence, we can study what we have in machine learning. And then within machine learning, we have a field which is a deep learning. So deep learning is a subfield of machine learning, uh, which makes the computation of multi-layer neural network feasible. I'm gonna explain to you guys what the deep learning is in conceptual. But we have already talked about different models for the machine learning. We're gonna talk about other possible models for deep learning. They're specific for deep learning, which is also part of machine learning. Okay, so let me give you guys a small history on artificial intelligence, machine learning, and deep learning. So the early um, ideas, implementations of artificial intelligence were made in 1950s, 1960s, 1970s, where they created this chess machine, right? That it was able to play was able to play chess with other people, or checkers, sorry. And then machine learning begins to flourish around the 1980s all the way to the 1910s, and then now since 2010 till now, we have seen the rise of deep learning, which is what we refer to the ChatGPT and other Google platforms. Okay, so that is deep learning thing. Thanks to deep learning is that we have ChatGPT. So traditional machine learning, what we have done is that we take these features of a specific data, we teach it to the machine, and the machine learns, classifies it as a cat. In deep learning, it works a little bit different. We have multiple layers of learning. So we have a deep low level features, and then that will take it, process that information to it, learn from a mid level features, and then from there it would send it to learn from a high level features, and then it will classify that as a cat. We'll see a little more examples about that, but you can see the differences of traditional machine learning versus a deep learning setup. That has a lot more layers on it. And I'm going to show you guys more examples about that. The scales of deep learning and process. So the performance, how much time does it take to be able to process a deep learning, and how much in comparison to the machine learning. So as you can see, the performance, so you can see here, traditional machine learning will be somewhere around here. It would take this much time. But if we want to do a deep learning, it would require a lot more from your computer to be able to process. So we require some CPU or GPU work to be able to perform those higher level deep learning higher level machine learning models like deep learning. So you can see here it will require a lot more work. Here's a little more in depth about the process of deep learning. So the first concept was actually introduced by Aristotle in 300 BC, introduced the association, started the history of humans' attempt to understand the brain. So that's when Aristotle, when the humans were trying to understand a little more how the brain functions. Alexander Bain in 1873 introduced the neural grouping as the earliest model of neural networks inspired by Havian learning rule. In 1943, McCulloch and Pitts introduced the MCP model, which is considered as the ancestor artificial intelligence model. 1949, Donald Hebb, considered as the father of neural networks, introduced the Havian learning rule, which has the foundations of model neural networks. In 1958, Frank Rosenblatt introduced the first perceptron, which is highly resembles modern perceptron. So I'm gonna show you guys an idea of a perceptron, but so this is very, very important. The first perceptron was a key factor to the process of deep learning, and so that one gets the reason that this is important is because the first perceptron in machine learning or in deep learning, right? Sorry, it's something that gets closer to the reality of how a perceptron in the real world works in your brain, how a neural network works. Paul Wertels in 1974 introduced the backpropagation, which is how uh, how the deep learning machine or model can learn from the mistakes, from the errors. So that's like reducing or learning how it would learn from the actual data that you submit. So that backpropagation is actually the part of learning. Tubo Kohenen and Konihiko Fukushima introduced self-organized maps, and then introduced the neo-coxitron, which inspired convolutional neural networks. That's another important model in neural networks. John Hatfield introduced the Hatfield network. Hilton and Sejnowski, introduced the Boltzmann machine. Paul Smolensky introduced the harmonium, which is later known as the restricted Boltzmann machine. Michael Jordan, defined and introduced the recurrent neural networks. John Lee Kuhn introduced the LetNet, showed the possibility of deep neural networks in practice. Schuster and Paliwo introduced the bidirectional recurrent neural networks. Hochreiter and Schmothuber introduced the long short-term memory, solved the problem of vanishing gradient in recurrent neural networks. Geoffrey Hinton introduced the deep relief networks, also introduced the layer-wise pre-training techniques, open current deep learning era. Salak Tikhonov and Hinton introduced the deep Boltzmann machines, and then Geoffrey Hinton introduced the dropout and efficient way of training neural networks. Okay, so that's a little bit of the history of how we have gone to 2022, which with deep learning and ChatGPT, right? Main types of machine learning. We talked about some of those, right? We said that in machine learning we can actually have supervised learning. We can have unsupervised learning, where kind of like the K clusters, right, or the K nearest neighbor. That's unsupervised learning. Supervised learning, we have the logistic regression, the linear regression, um, and many other ones. The On the types of machine learning, we have the self-supervised learning as well, and we have other ones that are reinforced learning, where you can actually teach the machine to be able to fix itself, right? Um, and then we have other fundamentals for the machine learning, some of them that we talked about. So we use data in machine learning to be able to learn, to teach the machine, right? Or the machine to learn. Humans learn by observation and unsupervised learning. So model of the world, common sense reasoning. So that's how we one way of teaching a machine, right, or a machine to learn is to, like humans, to by observation and unsupervised learning. Machine learning needs lots of label data to compensate. So in a machine learning, we need to be able to categorize the actual correct answer or the values or the classification of each of the features data. In machine learning, there's different setups, right? Different models. So tensors, generalization of matrices of n dimensions or rank in order degree. So we could have data that is 1 dimension, 2 dimension, 3 dimension, 4 dimensions, 5 dimensions tensors. In NumPy, an array kind of allows us to be able to do that. Now you might be thinking, okay, wait a minute, how 1 dimension, 2 dimension, 3 dimension, 4? What does that even look like, right? So don't think about dimensions as dimensions in the real world. Think about the dimensions as being represented by a feature. Remember, the features are, for example, if we want to predict the if we should buy a house or not in 2024, then we're gonna be looking at the price of the houses, the interest rates, the size of the house, right? The square footage, the number of rooms, the number of bathrooms. So those are features, data that we're gonna use to be able to analyze it. In other words, train our machine, our model, and be able to make predictions. So each of those are considered a dimension. Training, we talk about training, validation, and test split. So we still do the same thing, right? We're gonna train, validate, and test our data. We're gonna have mini batches, small sets of input data used at a time. We usually process independently, right? So we talked about having a K groups, right? Where we alternate what the actual validation is, so that we can have a better performance. Then we have model learning, training, inferences, right? We talked about having different models that require different type of parameters. So, for example, in a K nearest neighbor, K is a hyperparameter. We talked about the what else we talked about? Yeah. So some of those parameters, right? Some of the things that we talked about: generalization, right? Regulations. Models that with lots of parameters can easily overfit the trainer. So we have to be careful when we talk about parameters. Parameters and hyperparameters are different. The quality of a machine learning model is measured on new unseen samples. So we want to have it as many. We don't want to be able to have any leaked data between when we train our models. Regulations, any method to prevent overfitting, simplicity, sparsity, dropout, early stopping, other than adding more than that. So this is some of the tools that we use to be able to prevent it from overfeeding our model. There's such thing as overfeeding, where you overtrain your model, and when every time you add a new or predict something, it will be just based on the predictions on the overfitted model, which is going to give us the wrong prediction. So this is an example of overfitting. So now let's go into deep learning. What is deep learning? So deep learning is a very close resemblance of the neural network, neurons that we actually have as a humans. So you can here see perceptron. So you have the dentries of the neuron, and then a neuron has an axon, and then it has the terminal branches of the axons. So in neural network, we try to resemble that as much as possible. You can see the input, right? So you can see here all this being the input of your neuron. So your neurons are connected by other neurons, and we're passing charge there, and that charge will be processed inside your nucleus, and then it will be then passed on to the axon. And depending on the axon, if it passes the threshold value, it will then pass on to the other branches of your axon. So this is a very important part as well. This is your threshold. This is where it's going to determine if it passes the threshold to be able to pass on the information. If when you add all these values in your, if you add those values, right, these values, this of your dentries, and it's not enough to be able, there's not enough sum, right? When you sum it together, it doesn't give you enough to be able to pass over the threshold, then there will not be fire. There will not be a fire to pass on to the axon branches. So the sum has to be big enough to pass on the threshold. If it does pass the threshold, then the information does go through, and then it passes on the information to the next neuron. That's how the neurons work, and that's how we try to resemble, or they try to resemble the neural networks. So let's look a little bit more in depth on the deep neural networks. It's made of layers, input data and targets, loss function, and optimizers. So let me explain to you guys what that means. So in a neural network, we're going to have a component called the input value, like we had done before. And we're going to have our true values of the data that we're collecting. So we're going to put in our data through the input. Now this is going to have multiple layers of neural networks, and this is going to pass through another layer of neural networks, and then it's going to make a prediction. And then we're going to compare the prediction with the true values. We're going to compare them, and we're going to find out how much off are they each from each other. We're going to then take that value. This is our last score. We're going to try to optimize it, the value, and then train our weights. So we're going to modify our weights values so that the next time we pass on another data, the information through the layers and through the other layer, and makes the prediction is a little bit closer than the true targets. We want them to be the same. One of those two values to be the same as equally as possible. And then we're gonna repeat that. We're gonna figure out the last function, last score, and then we're gonna repeat that process again and again and again and again until we're done training. Okay, so I'm gonna put a pause here, and then I'll move on to the next one.